All right, hello, this is Mr. Huebner, and we are at the cafe, 1950 style, and we're working on intermolecular forces. So intermolecular forces are the forces between molecules, not within. Intra means the forces within a molecule, like covalent bonding and ionic bonds. That's intramolecular. But now if you're talking about water to water, molecule to molecule, it's intermolecular forces. So forces that keep different molecules held together. They're between two different molecules. These forces are what let us predict boiling points and solubility. You got the different types of oils with the WD-40, WD-20. That has to do with viscosity and what type of hydrocarbons are in there, and it has to deal with intermolecular forces. You don't want the wrong oil, the one that's too viscous or slow moving, therefore stronger intermolecular forces, in the wrong engine. So, and it actually does liquid become more viscous in cold or warm weather? Viscous meaning slow moving. Cold weather, yeah, that's why you have different oils for the cold weather as opposed to the summer. If you're a mechanic or into that. If you're me, you just go to the mechanic and have them change your oil for you. I can change my oil, but it takes too much time. So, all right, so there are three different intermolecular forces, and they're all essentially the same thing. The difference is the degree of its strength. And dispersion is the weakest, dipole dipole is a little bit stronger, and hydrogen bond is strongest. So just talking about dispersion first. Oh, it has the description right there. Electrons in nonpolar bonds move around randomly. So I would highlight nonpolar, because if you have something that's nonpolar, the only intermolecular force that's present is dispersion forces. At any given moment, there is a probability that they might be around one side of the molecule versus the other, creating a very temporary difference in charge. The more electrons that are in a compound means more dispersion forces. All right, so let's do fluorine, just for example. Fluorine has what, 7? No, well, outer valence, 7. Got 9 of them. Now we got fluorine. So at one moment, I mean, this is an extreme version. It's probably not going to occur that, but at one flash point in time, it could turn into that. And then what you're going to have is just for example, and then what we have is a partial negative, a partial positive, and it creates a stickiness or a force that is attractive. And is this partial positive, partial negative going to stay there permanently? Absolutely not. It's just a blimp in the trying to think of a blip of the eye, or a blink of the eye. There it is. Even less than a blink of the eye. It's there, like, basically not at all. But it does happen, and then it'll randomly form again, not form, and that's why the more electrons you have, it increases the probability of how you can have a disparity in charges. So if we're thinking fluorine versus chlorine, bromine, iodine, chlorine, bromine, iodine, if we're going down the list, the intermolecular force, dispersion force, increases as you get bigger. And this is just going down the halogens on the periodic table. All right, dipole dipole, it's the same concept. It's the only difference is instead of temporary, it's permanent. And when a molecule has a polar bond, that's when it's going to be a dipole dipole, because polar is unequal sharing of electrons, and that's permanent. We got let's do H2S. So S is more electronegative than hydrogen. So we got a permanent dipole moment moving towards the sulfur, which creates a partial negative. Here we got partial positive, partial positive. Technically, I should have put the partial symbol here. It's just a Greek symbol. Looks like an 8 with a piece of it missing at the top right. All right, and then what we have going on is another sulfur molecule, not a sulfur molecule, H2S molecule. And we got this stickiness between the partial positive and the partial negative. That's the intermolecular force called the dipole dipole. And why is it called a dipole? Because we have 1, 2, dies 2, we got 2 poles, a positive and negative pole. Dipole dipole means you got a positive negative and a positive negative. Again, same concept as dispersion force. The only difference is it's a permanent dipole moment. Hydrogen bond, same exact thing, only it's a stronger permanent dipole moment. So it's going to be with a covalent, polar covalent bond, but you got to have O, N, and H connected to hydrogen. So like H2O would be an example. Partial negative, partial positive, partial positive. Here we got the same thing. And we got this stickiness between the positive and the negative. So is there any difference? No, it's the same thing. It's a dipole moment that's created, and these charges, opposite charges of different molecules are connecting. Dispersion is super weak because the dipole moments are extremely temporary. Dipole dipole is stronger because you got a permanent dipole moment, and hydrogen bond is even stronger because it's dealing with O, N, and F. And if we look at the periodic table, it's the FON group, F-O-N. Those are the most electronegative elements on the periodic table. Therefore, the disparity between O and H, or N and H, or F and H, is going to be the greatest. And therefore, the charge that's produced is going to be a stronger charge. Therefore, a stronger bond. And then this kind of basically says what I said. Questions on that? That's intermolecular forces in a nutshell. Okay, then we got a few little practice things. I guess we'll probably get to allotropes maybe on Wednesday. Maybe we'll get to that. All right, immiscible means not mixable. Mixable. It's used in terms of describing liquids. So if we're talking about solid, it's soluble or insoluble. If you're talking about liquids, it's miscible or immiscible. If it's immiscible, it's not going to mix with that other liquid. Here's looking at different bonds. We got ion-ion, hydrogen bonding, dipole-dipole, dispersion. It's going from strongest to weakest. Technically, you could add a few more in here. You got ionic, polar, non-polar, and then you do hydrogen bonding, dipole-dipole, dispersion. Ion-ion, I would say is ionic. All right, how does molecular polarity affect solubility, melting points, and boiling points? Here's the application. Why does it matter? Intermolecular forces are huge in engineering, looking at biomedicine and all that stuff. So rank each of the highest to lowest boiling point. So the thing that's going to have the highest boiling point is going to have the strongest intermolecular forces, because they don't want to be released. They want to stick together, but when you boil something, you're pulling these molecules apart and turning them into a gas. So highest boiling point, highest intermolecular force. We got HBr, HF, HCl. Is there any hydrogen bonding that is going to occur? Like when we're thinking about HBr to HBr, is there hydrogen bonding? Or HF to HF, is there hydrogen bonding? So FON group, H with F, O, or N. Is F, O, or N here? There it is. Yeah, HF. So HF probably has the highest boiling point because it has the strongest intermolecular force. Because the other ones don't have H bonding, so therefore they're not going to be as strong. So rank from highest to lowest. Are they all going to be polar? Polar covalent? And you can answer that question by thinking, are they symmetrical? like split in half, H on the left, Br on the right. That's not symmetrical. So therefore they're polar covalent. So we're not going to have any dispersion happening. So now we're looking at dipole dipole. Now we got to figure out which one has a stronger dipole, which one is more electronegative, chlorine or bromine. Thinking that fluorine is the most electronegative element. As you go up and to the right, it gets higher electronegativity. So which one's more electronegative? Chlorine. You got it. Yeah, chlorine's more electronegative. So that's going to have a stronger dipole moment, therefore a higher boiling point. And then by default, HBr. So that's the last one. All right. Yeah, we'll talk about allotropes on Wednesday for sure. Rank each from the highest to lowest melting point. All right, melting point. Looking at this, it's kind of the same idea as boiling point. So we got CH4, H2O, H2S. First of all, are any of these, this is where it helps to draw the Lewis dot structure. If you can do it in your head, you can think, oh, I know this one's symmetrical, therefore it's nonpolar. CH4, can you do that in your head? Does that have symmetry? Yeah, it has symmetry, so that's definitely nonpolar. H2O, I know that one is what, bent? So it's not symmetrical, so that's polar. H2S is going to look the same thing, polar. So we got two things that are polar, one that is not. So the nonpolar one has just dispersion forces. That's the weakest. So in terms of melting point, it's going to have a high or low melting point. Low melting point because it doesn't take as much energy to break those intermolecular attractions. So it's going to have a low melting point. Makes sense because CH4 is methane. It's a gas at room temperature. So we're going to put CH4 at the end, each from highest to lowest. All right, then you got water versus H2S. First of all, can we divide these between hydrogen bonding and non-hydrogen bonding? Is there yeah, there's hydrogen bonding somewhere. If there's F, O, or N with H. F, O, or N. Is F, O, or N present here? Yes, there's an O right there. So that's definitely, water's going to have the highest melting point of these three chemicals. And then we got H2S. H2S is polar, so it's just dipole dipole. So as we go from highest to weakest, strongest to weakest intermolecular forces, we're also going from highest melting point to lowest. All right, then we got rank each from highest to lowest boiling point. Highest to lowest boiling point. Oh, that's the same as. Oh, wait, is that the same? Oh, it's similar. Similar. We got diatomic molecules. Same question, different molecules.
Does the diatomic make a difference?
It does, because all of them are nonpolar, so they're all going to have just dispersion forces. But some are going to have, like, what's the big thing here? We got F2 versus Br2. What's the big difference? The number of electrons. The electrons, number of electrons. So F doesn't have many. Bromine has quite a bit, 35 of them. So that means bromine's going to have a higher probability of forming that temporary plus-minus charge because it has more electrons. Therefore, it will form plus or minus charges more than F2. So highest boiling point is going to be Br2. And then we got Cl2, and then we got F2, which has the lowest boiling point. Which is, hey, that makes sense because bromine's actually a liquid at room temperature, so it's going to take more energy to boil it than something that's already a gas at room temperature. All right, rank the following from highest to lowest boiling point. Same question. Different molecules. We got neon, argon, but it's the same kind of concept. They're all going to be nonpolar if they were to actually form bonds. Which naturally they're not unless it's a weird exception. So then we go from biggest one, which is what, krypton? Yeah. Krypton to argon to neon. No, argon's smaller. But
no.
Yeah. All right, we got one more of these. Circle all of the following that would dissolve. Okay, so this is likes dissolves likes. If you are polar, you're going to dissolve in something that's polar. If you're nonpolar, you dissolve in something that's nonpolar. So oil and water don't mix. Water is polar. Oil would then be nonpolar. So, circle all the following that would dissolve in H2O polar substance. Here's a tricky one. NaCl has a permanent strong charge, plus minus charge. Is that similar to polar? Partial plus or minus charge? Yes. So the main idea is they both have charges. One is permanent and strong, and one is partial. So NaCl, do you think it'll act polar or nonpolar? Well, from our experience, does salt dissolve in water? Yeah, it dissolves in water. So therefore, it's going to act polar. Yeah, it's going to act polar. NH3, this one's tricky. Just writing it out, is this symmetrical? No, it's not symmetrical, therefore it is polar. So NH3 should dissolve in water. So anything that's not symmetrical or polar is going to do that. CO2, very symmetrical, so no, it's not going to dissolve in water. CF4, very symmetrical, not going to dissolve in water. OCl2, looks kind of like H2O, it's going to be bent. Sorry, going quick to beat the bell. There we go. It's there. Hey, CO2. We carbonate beverages all the time. That's so weird. It reacts with the water form carbonic acid, which then dissolves in water. Kind of loophole around it. So, all right, that is it. Hopefully you enjoyed that. See you guys next time.